discrete Fourier transform. Next time I do another topic, it's called fast Fourier transform, the second half of this topic. Yeah, still belong to the discrete Fourier transform, but there is a special case that we can do fast Fourier transform. Yeah, because later you have many software. The software doing FFT. What's that? Fast Fourier transform. FFT. Okay, so you need to have the basic knowledge. What's the FFT? So then you just run the program. Okay, so you get FFT. Yeah. All right. First, discrete. Why we go discrete? Yeah. So first, I need to talk about the importance of this discrete Fourier transform. We have the definition of Fourier transform on, convolution operations. Yeah. Before I do the discrete, let's complete this small topic, convolution. Yeah. We did convolution when we learned Laplace transform, right? Laplace transform, inverse Laplace transform. Then when we have convolution of two functions, Laplace transform of the convolution of two functions equals the product of Laplace transform of each of the two functions. Yeah. All right. Here, first, definition of the convolution. Yeah. Here, let me write the formula. Yeah. The definition, you saw the definition when you learn Laplace transform, but here, this version is slightly different from that version. So I will copy the old version, we can compare. Okay? Yeah, because here you can see when we take the integral limits from negative infinity to positive infinity. That's the main difference. Okay. The older version, let me copy here, Laplace transform of convolution, at that time, our definition is from 0 to t. The integral limit from 0 to t. All right, yeah. So that's the main difference. Okay, yeah. But their property is similar, yeah. Quite similar. Okay, yeah. Actually, you can imagine. Remember, we learned Heaviside function, right? If you use the Heaviside function, then we can write the older version as the newer version. Yeah. So here, let me use the Heaviside function. Okay, U function. Step function, unit step function, okay? So if I use that one, you can see our old version Laplace, convolution, we can define still on negative infinity to infinity, yeah. Inside function t, yeah. Because that t here we treat as a fixed number. Then unit step function, yeah, because non-zero from 0 to t, do you write u of t, yeah, right. So here we need to, because that t, we cannot use t, okay? So the tau, right? So let's use tau. U of tau minus U of tau minus t. Okay, d tau. Yeah, yeah. Because this part inside the brackets, non-zero equals 1. In this interval, okay? In the interval from 0 to t. Equals 1 in this interval, okay? Yeah. U of tau minus U of tau minus t, okay? Yeah. So here you can see, yeah, the special case. Yeah. All right. Yeah. Yeah. Anyway, but here you can see this is the more general case. From negative infinity to positive infinity, more general case. All right. Then, this time, we will apply Fourier transform on the convolution. Because this time it's not good to apply Laplace transform. Our Laplace transform, we have a range requirement. Okay? Range requirement. Yeah. And here, you know, our range is more generous. Yeah. All right. So then, here I just show you the formula. Yeah. All right. So the Laplace transform, we have that simple formula. Okay. Yeah. So this one. Yeah. Yeah. So, and our Fourier transform, we should have the similar formula, similar to this one. Yeah. Convolution. Yeah. All right. So here, look at the convolution theorem. Convolution theorem. Okay. So our convolution theorem, we apply Fourier transform on the convolution, but the right-hand side, there is a constant, root of 2 pi, this constant. Yeah. Because that constant, so here, related to the Fourier transform, the constant, I talked about the constant last time. Yeah. So if in future when you read books related to Fourier transform, different versions of the books, they may use the constant in different way. Yeah, so this is one way. Yeah, but other ways, you know, using the constant could be different. Yeah. Some there is no root. Okay. Yeah, different ways. Yeah. And just based on the different definition of the Fourier transform. First, the book you need to find the definition of Fourier transform. Yeah. So it's very common. Regarding the constant part, there are several different versions. So then, the definition of the Fourier transform, based on the different definitions, your constant here also different. Yeah. Your constant here also different. Yeah. I saw some versions, they try to use the appropriate constant in the Fourier transform definition to make this here 1. Yeah. So many versions, because they want to see the version Fourier transform on convolution should be the same as that of the Laplace transform, right? Constant 1, more natural, right? So you put this constant not equal to 1 constant, not quite natural. Okay? Some authors, mathematicians, so they feel, try to adjust the constant to make it 1 more natural. Yeah. All right. Yeah. Yeah. Anyway, so just a constant. Okay. All right. Yeah. But for our users, we as users, yeah. So when we apply Fourier transform, we need to know because you will use software. You know, when you work, you need to use software. You know, all those tools. But what's the definition of Fourier transform, right? So you want to see in that particular software tool, what definition is used for the Fourier transform, okay? Yeah. So that's some issue. So you need to, yeah, because there is no standard definition. Yeah. So you cannot call which one is standard. Yeah. You know. All right. Next, then we use the inverse Fourier transform to write this version. We take inverse Fourier transform both sides. Yeah, you know. Yeah. So there, you can see we have this another version. Yeah. Another version of the, related to the convolution. All right. Yeah. So that's the convolution theorem. Yeah. All right. And here we do not have time to practice Fourier transform. Yeah. Yeah. So yeah. So I just want to stop this topic here. So next we want to look at the discrete version. Yeah, that's important. Yeah. So in the real world applications, probably you will have more chances to apply to use the discrete version. Yeah. All right, so let me talk about this next topic, D.2, discrete Fourier transform. Yeah. So first, what's the meaning and why we want to discretize the function? Yeah. Oh, so I didn't make the animation. Yeah, I remember I did it. Yeah. All right. Okay. Yeah. Yeah. So first, all right. Yeah. So let me just do quickly. Yeah. Yeah. Yeah, because I need to explain. So mainly the ideas. Yeah. So the discretization idea. Yeah. Otherwise, it's not easy to understand ideas. All right. So let me look at the next slide. Did I do it? Yeah. Next slide, I did it. And animation. Okay. Yeah. Only this slide. All right. So let's do it. All right. First, let me write the question first. You know, what we are going to do. Okay. All right. The title, from analog to discrete. Yeah. Analog. So you know the function, analog function, it corresponds to a continuous function. So we most of the time we spend in this class, we work on the analog data. So the data given through continuous functions, even better. So differentiable, good functions. Yeah. But when you go to the current, so we can treat as the digital world. So we are in the digital world. Then most of the data we will deal with digital signals, digital data. Yeah. So that means we need to process our data through digital version of our given function. Yeah. Given function, what do we have? It's not a official definition of the function. What do we have? Basically a sequence of data as our digital version of the data. Yeah. Here, in application, a function f of x is given by a sequence of equally spaced sampled data points. Yeah. So that's the typical data form you need to process in the real world applications. Yeah. For example, images. Yeah. Images, you need to process pixels, right? So images basically a sequence of pixels. Yeah, but that sequence, 2D sequence. Okay? Yeah. So the variable part. Variable, you have two dimensions. X dimension, Y dimension. X coordinate, Y coordinate. And the function value, the grayscales, right? The grayscales, that's the function value. So for the images. But what do you have? A sequence of data points. Then, sound file, okay? So you listen to the music. What's the format of your music? So, Yeah, because the music is the digital music, right? Yeah. So we have the file. It's a digital file. Okay. So what do you have the file? Digital file. Yeah. Digital file. Then you can, if you use some software. So for example, MATLAB. So you can see the values, the sample values of a sound file. Okay. X coordinates, equally spaced sample points. Okay. Equally spaced sample points. Yeah. So the y value, the function value, that for the sound file, so you need to have certain y values, right? Yeah. So what do you have? A sequence of data points. Yeah. So here, our tools, we need to convert our tools from processing continuous function to digital data. Okay. All right. So we need to do a process. It's called a digitization. So we digitize the original function, f function. Yeah. So how to represent f function? A sequence of sample points. That's the form because when we collect data from the real world, we just get a sequence of sample points. Yeah. So we need to use devices to collect data points, right? Satellite, a lot of devices to help us collect data. But the data format collected sequence of sample points. Yeah. So that's the typical way. Right? Okay? So the hardware devices collect data in the real world. Then you can see we need to process digital version of the function. Yeah. Function, actually the original definition of the function is not available. Okay? Yeah. In the real world, you will never be given function definition. No function definition. Okay? Yeah. Because nobody knows the function definition. Nobody knows that. Okay? But you have sample points. Okay? Hardware devices collect. Okay? Sensors, a lot of sensors, cameras, collect these data points. Yeah. So we need to process that form of data. Okay? So, yeah. So for that reason, yeah. So I want to, give you background information. Yeah. Oh, let's look at the math. How do we understand? How do we make our tool? So here our tool is Fourier transform. How do we convert our Fourier transform tool on this digital data sets? Okay. Question. How to approximate the function f of x with a convenient function? Yeah. Yeah. As I said, the original f function is not given. Yeah. That f of function, no definition for the original function. Yeah. But we want to represent original function. Otherwise, we cannot do anything. Okay? If you want to apply mathematical tools on the original function, the first thing you need to do, you need a function representation. Right? Yeah? You need a function representation. Okay? Yeah. Yeah. All right. So the function representation here, we can only use the approximation way. Yeah. Because you cannot expect you get exact representation. Yeah. Because nobody knows the exact representation. Okay? Yeah. People can only do approximation here. Okay? All right. So for the approximation, you have a lot of freedom, right? Yeah. Because how do you approximate original function? You have a lot of freedom to choose. different ways to approximate. Yeah. Here, we have one way, a special way to choose the approximation. It is, so the answer for this question, use a complex trigonometric polynomial. Complex trigonometric polynomial. Okay? Yeah. So you may ask, so why we use complex trigonometric polynomial? Yeah. Here, look at the assumption. Our assumption of the original function is a 2 pi periodic function. Yeah. So when you model a 2 pi periodic function, you want to use some also 2 pi periodic fundamental functions, right? Yeah. So sine, cosine, the best candidates for 2 pi periodic. Yeah. But sine, cosine, these two, we should use sine, cosine together, right? Yeah. Yeah. We should not only use cosine, only use sine. Yeah. Because if you only use sine or cosine, it's not complete. The system is not complete. You cannot represent all the information you want to represent. It's not complete. So we want to use a complete system to represent the given data. Okay? So what's the complete system? Yeah. So remember last time, the trigonometric system, 1 cosine x, sine x, cosine 2x, sine 2x, and so on. Yeah. That's a complete system. So we should use all those functions. Yeah. But all those functions, to integrate sine, cosine together as one function, that's the complex trigonometric way. E to the I pi x, right? E to the function. That E function, here we use the complex form, but we integrate sine, cosine together in one function. In one function. So that's the reason why people choose the complex form. Yeah, because you put sine, cosine together. Okay? So you integrate sine, cosine into one function, one E function, covers sine, cosine. Okay? So that's the convenience. All right. Here, the complex trigonometric polynomial, that's this form. Okay? The general form. Yeah. Here. Yeah. Polynomial. So why we call polynomial? Yeah. Yeah. So here you can see the E part that corresponds to, because polynomial, it's a x to certain exponent. Yeah. It's a monomial. Yeah. Here you have the same form, but trigonometric. So E, you have sine, cosine. So we call it trigonometric polynomials. Yeah. So not algebraic polynomial. Here we are working on trigonometric polynomials. Yeah. Not algebraic polynomials. Okay. All right. Then the next question. Here you have freedom to choose the coefficients of this trigonometric polynomial, but you have a lot of freedom to choose the coefficients. But what's the best choice? Think about how to choose those C coefficients to get good approximation you want to have. No, you want to approximate original function well. In what sense, right? Yeah. In what sense you mean your approximation? So you feel it's a good approximation. Yeah. So here, because when we define approximation, there are many different meanings. There are many different meanings. Yeah. Yeah. Here, there is one special meaning, so we call the interpolation. Yeah. We approximate original function, we use the data interpolation. Yeah. So this is a commonly used method. Data interpolation. Yeah. So what's that? So the concept of data interpolation. Yeah. Concept, data interpolation. Yeah. You plug in. Yeah. So here you have capital N here. Capital N. How many data samples do you have? Capital N, right? Yeah. look at how many data samples do you have here. A sample, subscripts, k from 0 through n minus 1. So total, you have n samples. All right, sample points, n sample points. The interpolation requirements tells us when we plug in those n sample points, the function values given. Little f, function values given. The function values should be the same as our trigonometric polynomial function values. So they match. So these two functions, there are two different functions. F of x, original function. Yeah. But its formula not available. Okay? So nobody knows its real formula, original function. All right? But here we use some model function. Yeah. So, yeah. If we do not know the original function, so we try to find a way to approximate. Yeah. So here the model function. The model function is a trigonometric polynomial. Okay? Yeah. So we know our trigonometric polynomial is not exact original function. Yeah. So we do not expect that. Yeah. So there is some difference. Yeah. But the requirement, interpolation requirement here is these two functions match exactly at those capital N data points. How about that? They match exactly. Yeah. We set up equations to make them the same values. Yeah. Yeah. So they approximate in this sense. How about that? Yeah. Some natural way, right? Yeah. So we can treat it as a natural way. Okay. All the given data sampling locations, these two functions match exact. Okay. So yeah, that's the interpolation meaning. Okay. All right. The question is, under this interpolation requirement, can you find coefficient little c, all these little c coefficients? Yeah. So that's a linear algebra problem. Simple linear algebra problem. No, straightforward, simple linear algebra problem. Okay? We just solve a linear equation. Here, solving a linear equation, so you get all those c coefficients. All right. So how to solve? Yeah. So next, so let's work on this linear system, n by n linear system. How to determine the coefficients of these little c, n coefficients. Yeah. All right. Formulas for discrete Fourier coefficients. After we calculate the formulas for these c coefficients, that's our discrete version of Fourier transform. That's simple. Okay? That's simple. Yeah. C coefficients. Okay? Yeah. So we will get a discrete Fourier transform. Data. All right? Yeah. Oh, yeah. So now this one. Here. Okay. Formula for discrete. Yeah. Here. So let me just copy the original form here. Okay? Yeah. All right. So you know the notations here. All right. Now we need to calculate. Yeah. So here I give you the result. Yeah. Because the derivation, on the textbook derivation. Yeah. Yeah. But if you understand, you need to do some, non-trivial computation work. Yeah. Yeah. So there is some identity you need to prove. Sine, cosine, identity, you need to prove. Yeah. 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 So I skip that part. Okay? I skip that part. So here I just give you the result. Okay. All right. So the result is, you can see the formula is very nice. Okay? The formula, right? So similar to our original expression, trigonometric expression. Trigonometric polynomial, we have an expression. Yeah? Trigonometric expression, right? Look at the way to calculate each constant c sub n this formula. Okay, so you compare, right? Yeah. So the format, the structure, we can see the structure, very close structure. Okay, yeah. It can be proved in that way. All right, so here we just use this result. Yeah. This result, we treat it as discrete Fourier transform, but we change slightly. Yeah. We change slightly on this coefficient. Yeah. So here, so there is some constant adjustment. We change that part, constant adjustment. So now the definition of discrete Fourier transform, this formula, okay? Yeah. F n hat. Yeah. F hat. Yeah, here the Fourier transform we use hat notation. Yeah. Yeah. All right. Equals n times C sub n, then the summation of this, another, we used trigonometric polynomial representation, but here you can see we plug in xk value into this trigonometric polynomial. Okay, yeah. F n, yeah. So here, yeah. So n is fixed. When we calculate f n hat, n is fixed, but we do summation, on the subscripts k from 0 to n minus 1. Yeah. So that trigonometric. Yeah. So here, actually, so although you see the form like a trigonometric polynomial, but actually it's not a trigonometric polynomial. Yeah. Because these k changes. Okay. These k changes. Yeah. Trigonometric polynomial, your variable x, you plug in, it should be fixed. Yeah. So the format, the format has some close relation, but it's not exact that trigonometric polynomial. Yeah. All right. Yeah. So the discrete Fourier transform. Yeah. Yeah. So now, let me talk about the importance of this version of Fourier transform, discrete. Yeah. All right. Yeah. So let me give you the notation, the basic notation. Given signal, yeah, here, the version. So we call, so the data here we call signal. Okay? Yeah. So, question?
I have a question. On that formula for the exponent on E, is that negative in x sub e?
Right. Here negative. Yeah, one side negative. Yeah, you're right. One side negative, one side positive. Okay, yeah, good. Yeah, yeah, because one side, this side negative, right? This side negative, right? Yeah. The inverse, sorry, this side negative. Then the inverse side is positive. Yeah. Oh, yeah, here, yeah, negative. Yeah, good question. Yeah, later, because we will change the sign. Yes, you're right. Yeah. One side negative, then the next positive. Yeah. All right, so when I copy, so I didn't. Yeah. All right, notations. Yeah, all right, so here. Yeah, because here, negative. Okay? Yeah, so here, negative. But later we change to positive. Yeah. So, all right. Yeah, good. So we made, yeah. All right. Let's start from here. Given signal f, the signal, a sequence of values. Yeah. So we treat it as a vector, okay? The column vector. Then we apply discrete Fourier transform formula. Yeah. Discrete Fourier transform formula. So we get the Fourier coefficients. Fourier coefficients, another vector, the same dimension, n dimension. Okay, so we do not change dimension. Yeah. Given n-dimensional signal, so then we do discrete Fourier transform. We get another n-dimensional data, but in different domain. Yeah, here, domain is different. So we change the domain. After the Fourier transform, we from the time domain to frequency domain. So here, all these frequency, each number we treat as one frequency, coefficient. Coefficient correspond to one coefficient. So here we call it frequency spectrum. So covering all frequencies. Spectrum means not just the one, some of them. We cover all the frequencies. So that's the spectrum. Okay? All right. Yeah. Then notation. When we do the calculation notation, this E representation is a little complicated, right? E to the, you need to write a lot of things. So we introduce a little w to represent this whole E thing. Okay? Yeah, so negative here. All right. The whole E thing. All right. Then all those E terms, we can use the little w to represent. Yeah. All right. So we define a matrix, special matrix. All right. So here, the discrete Fourier transform. Yeah, we write a formula for the discrete Fourier transform in the matrix equation form. So this is matrix form. Okay. F hat vector equals capital F sub n, this n by n matrix, times the original signal vector. This F is the signal vector. Okay, that F, capital Fn, that n by n matrix here we use W. Yeah. So W notation. Yeah. So the negative sign. Yeah. So the Andrew pointed out the negative sign here inside the W. Okay. So the W is exponent. There is no negative sign. Yeah. But inside W you have that negative sign. Yeah. Okay. You have that negative sign. All right. So then it's a square matrix. So you have row numbers and corresponding to the row numbers, K corresponding to the column numbers. Yeah. So that's the discrete Fourier transform. Okay? So you do a matrix multiplication. So you get a discrete Fourier transform. Yeah. All right? Yeah. Discrete version. All right. Yeah. So here, this capital F sub n, we call a Fourier matrix. Fourier matrix. So those W, yeah, so all those W Fourier matrix. Right. Then, inverse discrete Fourier transform. Yeah, because after we work on the frequency domain, so we do some data processing, then after we finish the processing, we need to go back to the original time domain. Yeah. So when you go back, you apply the inverse discrete Fourier transform. So you take the inverse matrix. Yeah. F equals the inverse of the Fourier matrix times the frequency coefficient vector. Okay? So the coefficients vector for the frequency spectrum. Yeah. The inverse. Yeah. But the question is, what is the inverse of the Fourier matrix? So we want to know, yeah, because the inverse, if you do calculation, it could be very complicated. Yeah. Think about, especially, so here, this inverse, so we want to find its specific form. We don't want to calculate matrix inverse at the, in the real time. In the real time, matrix inverse calculation, very expensive. Yeah. Especially where our data samples, the number of data samples very large, the n number very large, you calculate a large inverse matrix, it's too slow. Too slow. So we don't want to do that. All right. So now, the good thing is here is we have formulas to calculate matrix inverse. Yeah. All right. So next, let's find the formula for this Fourier matrix inverse. Yeah. All right. Yeah. First, here we use the complex conjugate of a complex number, z. A plus bi, its complex conjugate is, here we use bar, z bar, okay? Z bar equals a minus bi. Yeah. You just change the sign. You just change the sign of the imaginary part, b imaginary part. From plus to minus, that's the conjugate, complex conjugate. Okay. All right. So with this notation here, a and b are real numbers. With this notation, then our W bar, yeah, because when we take the complex conjugate operation on our Fourier matrix, we need to take conjugate operation on the W. Okay, so W bar this time negative sign is gone. Yeah, so that means that for the inverse, you need to use the version without negative sign. Yeah, inverse version. Yeah. Here first the W version, no negative sign. Okay, the conjugate cause that. Okay. Then capital F bar Fourier matrix bar conjugate. So you use the W bar, as your base. Yeah, as your base. So then you form that special matrix. Yeah. Yeah. So that matrix is what we call, Van Neumann matrix. Yeah, the structure is the Van Neumann matrix. Yeah. But this time we use W bar to form that, special Van Neumann matrix. Okay. Key property here. So to get the inverse, there is a key property. Okay, nice property. So one want to use. That is F bar sub n matrix multiplication, n by matrix multiplication times Fn, or you change the order, you get n times the identity matrix. N times the identity matrix. Yeah. So this can be proved, formula. Okay? Yeah. So on the textbook there is a proof. Yeah. Yeah. So here I skip that proof. Not too hard. Yeah. Yeah. But then you need to, do some computation carefully. Yeah. All right. From this formula, we can write inverse Fourier transform formula, because we can write the inverse Fourier matrix using that F bar. F bar corresponds to the inverse Fourier transform. But taking conjugate, here we don't take the transpose, we just take the conjugate. Yeah. Conjugate, all right? Yeah. Take the, when you calculate, student, join us. When you calculate inverse Fourier transform, we know usually the computation is very expensive. Yeah, so it takes a lot of time, But here, when you apply the formula 1 over n, the constant times conjugate of the matrix, that's very easy, right? That's very fast. Yeah. So you just, for each entry of the matrix, you just make it conjugate version of the complex number. Yeah. Yeah. So that way you get an inverse matrix. Okay? That simple way you get an inverse matrix. Okay. All right. Yeah. So then, here the example. Yeah. So here is a 4x4 example. Yeah. So we apply Fourier, discrete Fourier transform. How do you apply? You need to form this 4x4 matrix. Okay, yeah. So the matrix entry structure. So based on the structure, all right. So then you do multiplication. Yeah. So you get a Fourier coefficients. Yeah. Coefficients for the frequencies. Okay, for the frequencies. Yeah. Then, if you want to find inverse, so you can take this matrix and make its conjugate. Conjugate for real numbers, you do not change anything. For complex number, you change the sign. Yeah. Negative I, you change to I. Change the sign of the complex numbers. That's the, bar version, conjugate version. Okay? And 1 over n, 1 over 4, you multiply to this side, you get the original signal. Yeah, you get original signal. Okay? Yeah. So that's the, discrete Fourier transform and inverse discrete Fourier transform. Then, because after you do the transform, then you do signal processing at the frequency domain. Yeah. So a lot of applications, you do signal processing like a denoising, like extract features. So you work on all those, special applications at the frequency domain. Okay? Yeah. After you complete the processing at the frequency domain, then you apply inverse discrete Fourier transform back to, so you go back to the time domain. Yeah. So that's your processing result. Okay? For example, denoising. So you remove the noise. Okay? Yeah. So you see your signal, so a lot of noise removed. Yeah. So that idea. Okay? Because if you work on the time domain directly removing the noise, very hard to, because mixed noise and the signal content mixed, hard to separate. But when you convert to transform to frequency domain, the noise and the signal content separated in different frequencies. Yeah. Usually noise appear in the high frequency, not low frequency. Okay, high frequency. Yeah. So one simple way, you just cut off high frequency. Cut off. Although you lose some high frequency signal content, you lose a little bit. Okay, high frequency. Then you convert it back to original signal. Yeah, you can see a lot of noise removed. Yeah, cut off high frequency. Yeah, that idea. All right. Yeah. All right. Yeah. So that's the this idea. So let's stop right here for this topic. Yeah. So next time I talk about fast Fourier transform. So that's the continuation of this topic. But the question is, how do we calculate the matrix multiplication, multiply the signal vector faster? Yeah. Fast Fourier transform, extremely fast. Okay? Yeah. So we do next time. Yeah. Fast Fourier transform. Yeah. All right. Yeah. Positive, when we define original trigonometric polynomial, it's positive. This is original trigonometric polynomial. So no reason we choose negative, right? Yeah. But when we do transform, when we do operation, as a result, we get a negative. Yeah. So when we apply the discrete Fourier transform, the result, we have the negative. Yeah. All right. So before we apply the Fourier transform, no negative. All right. And at this step, there is a Fourier transform. Yeah. Because this, after the computation, as a formula result, this negative sign comes out. Okay. So this here, it's a negative. Then, because this coefficient is closely related to the the frequency of the discrete Fourier transform. Yeah. So because we take this version, you just multiply by n. So also negative. Yeah. All right. So then later, all right. Yeah. So here, because W, we want to represent this side, this formula. So the W represent this formula. So the W has this negative sign. Yeah. And W, we use W in this matrix, capital Fn. So this matrix has that negative sign. Yeah. All right. Yeah, so W here, the negative sign. Yeah. Then the inverse Fourier transform. Yeah. Inverse Fourier transform. Then the next slide, we take the conjugate, complex conjugate, yeah, change the sign. Yeah. So the W bar, the negative sign is gone, yeah, because we use W bar, we want to do inverse Fourier transform. So in the inverse Fourier transform formula, no negative sign. Yeah. No that negative sign. Inverse. Okay? Yeah. So the inverse matrix, we use this F bar matrix. Okay. F bar. After you take a bar, the negative sign is gone. Okay? All right. Yeah. So here, this matrix, inverse. Yeah. So F bar, so you use the positive sign. Yeah. So in the E exponent, you use the positive sign. Yeah. All right. Yeah. So after, we, carefully we keep track of the, the sign change. So now we know which side negative, which side positive. Yeah. So for Fourier transform, discrete Fourier transform, when you apply the formula, use that negative sign. But when you apply the inverse Fourier transform, you use the positive sign. Yeah. So in that way, so you can, because you can get the idea, so we can recover the original signal. So one time positive sign multiplication, another time negative sign multiplication, you have cancellation, so you recover to the original signal. No. So that logic, so that structure, can explain why we can recover, right? Why can we do the Fourier transform and the inverse Fourier transform? We can go back to the original signal. Yeah. All right. Yeah. So that's the this important operation. Yeah. Next. Here.